Shachar, are you about ready?
1 second.
Sure.
Yes. Can you hear me?
Yeah.
Perfect.
Cool.
Good.
Okay. Well, yeah. So let's give it maybe just a minute. Yeah. Okay. So we've got 44 people here. That sounds like a quorum. Yeah. So welcome back, everybody. We're very happy to have Shachar Lovett speaking today. Shachar is an associate professor at UC San Diego. Before that, he was a postdoc at IAS until about 2012, and before that, he received his PhD from Weizmann. And Shachar works broadly across CS and math, in particular in complexity, randomness and pseudo-randomness, algebraic constructions, coding theory, additive combinatorics, and high-dimensional geometry. And today he's going to tell us about point location, an interface between geometry, machine learning, and complexity. Yeah, so thanks very much for being here, Shachar, and take it away.
Thanks, Mary. Thanks for the nice introduction and the invitation to speak here. And again, I want to talk about point location, which is a problem I started getting interested in a few years ago. And I want to tell you about some interesting connection it has between geometry, machine learning, and complexity theory, and maybe also other fields. And again, I really invite people who have any questions, just stop me and ask. I mean, if this can be interactive, it's going to be ideal. And this is all based on several joint works with several great colleagues, Max Hopkins, Daniel Kane, Gaurav Mahajan, Shai Moran, and Jiapeng Zhang. Okay, so what I want to tell you about today is basically problems that arise in 3 different fields. In geometry, this is both computational geometry, but also discrete geometry. In machine learning and in complexity theory, and somehow point location is going to be the common thread between all 3, although sometimes in disguise. So let's start with a point location problem in geometry. And it's a following sort of simple looking question. So you are in some d-dimensional Euclidean space, RD, but again for concreteness, and so it's easy to draw just look at the plane here. And you have a partition of the plane or of space given by hyperplanes, which are these blue lines here. So there is sort of breakup space, into regions, and which could be either bounded, like this triangle here, or maybe unbounded, like this sort of area here, so like polytopes or polyhedras. And this is not part of your input. This is what defines your problem. Your input is going to be some point. Like in this case, it's going to be this red point here. And your goal will be to find the cell where this point is. Like in this case, it's going to be this shaded triangle. So somehow your goal is to find this triangle. And again, I'm sort of being a bit vague here. What do I mean by finding it, and exactly how do we define this area? But this is like on the conceptual level the problem. So you're given a partition of space by hyperplanes, and you want to find the region where your input is. And now the model that we'll be studying here is a computational model called linear decision trees. And in this model, you don't have direct access to the input point. Remember, the input point is the only thing you don't know. So the only access you have to this input point is via queries. And these queries are hyperplane queries. So you can choose a hyperplane and query the point and see if it lies on one side or another side of this hyperplane. So let me show you an example. So here's a problem. Maybe initially I choose to query this line, and I get the answer that my point lies below this line. So now I know my point is somewhere in this shaded area. And then I can say, give me this information, I'm going to query this line next. And now I know that my point must lie in this shaded area, at the intersection of the 2 half spaces. And now I decide, well, let's query this line, and now I know my point lies in this triangle, and I'm done. So in this case, I was very lucky. I sort of chose 3 lines that happened to exactly correspond to the, cell I'm interested in. But, in more generality, you could ask, well, how many queries are needed? And also here, I'm restricting myself to only query the lines that define the partition. But more generally, you could ask, maybe it makes sense to consider other lines, not ones that define the partition, which maybe, if you've never thought about this problem, might seem very, ridiculous. Why would I do that? But we're going to see examples of why this is useful. But this is a problem. So now we're happy. We found this area. So let's write another one more, word about the model. Why is this called the linear decision tree? Well, it's because of the different way you can view this model, which actually looks like a tree. So you can think of this algorithm as a ternary tree, meaning you have queries, and each query has one of three possible answers, where internal nodes are just linear queries. So imagine my input point being, x1, x2 up to xn, some point in RD, so x1 up to xd, and a hyperplane is just asking a linear query. And I'm asking, is this answer going to be negative, 0, positive? And based on that, I'm going to move down the tree. And you can see that somehow the depth of this tree is just the number of queries you make. And my goal is to just minimize the depth of this tree, or minimize the number of queries you make. And now let's try to slightly more formally define the model. So although you could consider general hyperplanes, I mean, it's going to be easier notationally to just restrict myself here to homogeneous ones, the one that go through the origin. Because if you have non-homogeneous ones, you can also just embed them in dimension 1 more. So it basically looks the same. So my hyperplanes is going to be the set H of H1, H2 up to Hn of hyperplanes. And these are just the normals of the hyperplanes. And they're all in RD. And remember, the hyperplanes are not part of my input. This is what defines the problem. So I know them. The only thing I don't know is the input, which is this point in RD. Now, what is a cell? Well, I claim that the cell of X is determined by knowing for each hyperplane here if X lies below it, above it, or exactly on top of it. So it's going to be, you take the inner product of Hi and X, and that's just going to be either negative if X lies below the hyperplane, positive if X lies above it, or 0 if it's exactly on top of it. So I take this inner product, I compute its sign, which is something -1, 0, 1, and I do it for all n of them. So of course, this could be very redundant, right? This is, I mean, it's a very redundant way of representing a cell, but it's definitely sufficient. And again, to information theoretically, at least, computing the cell of the point X is equivalent to computing this vector in -1, 0, 1 to the n. So I'm going to denote this AH of X. So it's a cell of X with respect to the hyperplane arrangement H. And how am I supposed to do it? Well, I'm allowed to make queries. And the queries I'm allowed to make is the sign of H and X for some H that I choose could be one of the hyperplanes I got, or if I feel lucky, I might choose some other hyperplane. And again, at this point, it might seem like, why would I choose any other hyperplane? But we're going to see examples why this is useful. And there are going to be two natural, let's call them combinatorial questions here. One is going to be, well, how many queries are needed to compute this function? So of course, one very naive way would just be to go through these hyperplanes one by one and compute the sign. That's going to be one way to do it. But we're going to see there are much better ways, much more efficient ways of doing that. And the other one is going to be, does it help to query arbitrary H in RD? Or maybe it's enough to just query H in H, or maybe something else that's slightly more general. So what queries should we make? Now, there are going to be various other algorithmic questions that we could discuss, but for the sake of time and to keep this concrete, I'm just going to be focusing on these combinatorial questions in this talk. And I'll also address some of the algorithmic questions maybe towards the end of the talk. So for the most part, our goal will be to try and understand these two combinatorial questions. And in particular, the first one, what's the query complexity of this problem? And now here's the simple bound. And let's just recall the setting. So we have these hyperplanes, n of them. So again, fixing notations throughout the talk, we're always going to work in dimension D. And we're always going to have n hyperplanes. So these are the two parameters, the number of hyperplanes, n, and the dimension D. And my goal is to compute the cell here using a few queries. So here's a very trivial upper bound, query all n hyperplanes. Of course, that's going to work, but can we do better? So let me show you one simple lower bound here that shows something like what's the best you could try to achieve, and that you need at least something like d log n queries for, let's say, general hyperplanes. So why is that? Let me show you the proof here. So here's a proof. So if I have n, let's say, generic hyperplanes, without at least a specific structure, they partition RD into some number of cells. And if you do some computation, this number of cells is n to the d. Like, for example, if I have n lines in the plane, they partition the plane into something like n squared cells. Now, so my answer The cell is one of these n to the d possible answers. However, every query I make has only 3 possible answers, -1, 0, or 1. So if I have queries that only return one of 3 answers, and at the end the number of possible answers is n to the d, I need at least log of the number of answers. I need log of n to the d, so like d log n. So you see, this lower bound completely ignores the type of queries we make. We make sort of these linear queries, and this shows that if any type of query where you only have a constant number of answers, you need d log n. So then now the question is going to be, we know that we need d log n for like arbitrary queries, and we have this trivial bound of n queries for like, linear queries. Which one is correct? Think of d as small as n as big. Do we need log n queries or do we need n queries? So this exponential gap here. Yeah, actually I can't even see my bottom point because Zoom is hiding what's going on here. So, but anyway, which one is the right answer? Okay, so now let me move to a different area of machine learning, in particular the area of active learning. And as you'll see, you basically get the same problem in disguise by studying this problem of active learning in machine learning. So what is active learning? So it started from the following of realization that people had a while back, but it's becoming even more relevant today, which is it is very, very easy today to just get huge amounts of unlabeled data. So I mean, let's say that you want to do some image analysis, and it's very easy to get images. Just go on Instagram and download tons and tons of images. Or if you want to analyze texts, short text, go on Twitter. 500 million tweets every day, tons of them. However, if you want to apply like fancy algorithms like deep learning, most of them need labeled data. So like if you want to analyze text and you want to analyze some specific, question you have about text, like the topic, for example, then you need some person to go and like label this text. And this, of course, takes time. So we don't want to ask people to label 500 million tweets every day. So the whole point of active learning is to say, labeling data is expensive, so we should sort of choose carefully which data items we want to query, or in this case, to label. So that's basically the premise of active learning. Active learning says we have a learning algorithm that gets a large amount of unlabeled examples, basically infinitely many. And it can choose which of these data items, these examples, it wants to query. And querying here is an expensive part. So imagine you're downloading these 500 million tweets, and you can send them, via Mechanical Turk to people to label the topic. So everything like that, every query costs you money, but downloading is basically free. And this is in contrast with maybe, let's call it passive learning, where you just get tons of labeled examples. And again, the hope will be that if we smartly choose which examples we query, we can query only a few of them, not all of them, and still do relatively well. So let's try to model that. So we're going to model that by considering the problem of learning half spaces. So I have data points, which are just going to be some set of points in R to the D, in some feature space, d-dimensional feature space. The input is going to be some hyperplane in RD, which is my classifier. And in this talk, I'll be assuming that the classifier never makes mistakes, right? And so the label of a point is going to be the sign of h and x. So I'm going to take my data point in RD. I'm going to take my hyperplane. I'm going to put it in a product, it's positive or negative, plus or minus, that's going to be the sign. And my goal is to label all these points in X. And also here, we don't have direct access to the input hyperplane. I mean, this is a classifier we're trying to learn. So what can we do? We can make queries. So we can like choose maybe a point in my data set, send it to a user, and the user is going to tell me, is this plus or minus? So it's going to give this binary classification. Or maybe we can sort of create new examples for the data points and send those to the user. And my point is going to be that, first of all, these two questions are basically the same. This point location question in geometry and this active learning question in machine learning are the same mathematical question in basically just by duality. So why? So the point location problem in geometry is where we know the hyperplanes at partition space. We don't know the point that we're trying to figure out which cell it is in. My goal is to decide the cell, which is just determined by all these signs of X and all these hyperplanes in H, And the method is just adaptive linear queries. I can choose a query, a linear query, and query the point x. And active learning is exactly the same question, where we just dualize points and hyperplanes. I mean, just replace in your head h with being hyperplane of being points and x with being a point between hyperplanes, and you get exactly the same mathematical question. So you see, studying these two questions is basically the same math question. So what did we gain from that? So the one thing we gain from that is that usually, the natural things to try to do when you study a problem changes when you change your viewpoint. So when you study this question from this point location viewpoint, so this question was mostly studied in the computational geometry, discrete geometry community. So you do things that are natural to do when you study geometry, like space partitioning in various ways. When you study the second problem, although it's the same problem, because it comes from machine learning, then you do things that are natural for machine learning, like, for example, boosting. So the type of techniques you might try to apply changes depending on how you view the problem. So even though these two are the same problem in disguise, it sort of lends itself to different techniques. And in this talk, I'm going to focus on this sort of second viewpoint, this active learning viewpoint, because first of all, I think it's more intuitive, at least for me it is more intuitive. And also it's more amenable to machine learning techniques, which are going to be useful here. So we're going to take this sort of second viewpoint. And let's see, what can we do? How can we hope to beat this naive bound? Like also here, if you go to this active learning viewpoint, the naive thing to do would be to just try to label all my data points. Take all my data points, endpoints, and just label all of them. But that's going to be naive. So we'll try to do better. So let me first show you a very simple example why you can hope to do better. That's going to be the one-dimensional version of active learning. So here is the problem. So you're given n points, unlabeled points, on the real line in one dimension. And you label these points plus or minus 1 as follows. There is an unknown threshold that you don't know. Here's this green line. Everything to the right of this green line, you're going to call a plus 1. Everything to the left, you're going to call a minus 1. And you know these points, right? I mean, you know the data set. The only thing you don't know is the classifier, in this case, this threshold. So what you really are given is these points without labels. And your goal is to make few label queries, not query all of them, but just few of them. And then somehow, from the queries you made, you want to infer the rest of them for free, without making any more queries. And of course, when you view this one-dimensional problem, the natural thing to try to do is binary search. So if you do binary search here, this would work very well. So let's see why. So you start by querying the middle point. And let's say I go to plus 1 here. Then I know for free that all the points to the right of it must be a 1. I don't need to query them, they have to be 1. And then I query the middle point of the points I have left. In this case, this one's a minus 1. So I know all the points to the left of it must be a minus 1. And then I just keep going. All right, so I do binary search every time. So to correctly label endpoints in one dimensions, we just need to query log n. So we get this lower bound of log n. And we just infer the rest for free. So at least in one dimension, we can do much, much better compared to querying all the points. Of course, one dimension is a very, very toy problem. So the question is, can we hope to generalize this binary search approach to higher dimensions? And we're going to see now an example showing that already when we move to 2 dimensions, we're going to have some problems. And that's going to be an example by Sanjay Dasgupta from, I believe, more than 20 years ago. So here's a problem of active learning in 2 dimensions, and it's going to show some limitations of this approach. So again, what is a problem? So it's going to be very similar to the one-dimensional problem, except now we're in 2 dimensions. So we're given n unlabeled points, but now they're in 2 dimensions. So again, all these black points here, this square, and you know these points. The only thing you don't know is this green line here, going through this plane. And I'm going to label all the points, above it as minus 1, all the points below it as plus 1. Okay, that's it. So your goal is to figure out which ones are plus 1, which ones are minus 1. But of course, you don't get to see the green line. What you get to see is just the points. And now I'm asking you, well, how can you solve it? And when you first see this problem, you say, well, of course, there should be a way to do it. Maybe I'm first going to sort them on the x-coordinate or do binary search on the x-coordinate and the y-coordinate. So it seems like there should be a way of generalizing binary search from 1 dimension to 2 dimensions. But this picture is misleading because there are examples where you cannot do that. So I'm going to show you now an example where you need to query basically all the points. And here's the example. So imagine that all the points are sitting on a circle, or maybe more generally in convex position. And I'm giving you the promise that your line, your unknown line, separates exactly 1 point from the rest of the points. So one point gets labeled +1, all the other ones get the label -1. And basically I'm asking you which point got labeled +1. Well, of course, if you're only allowed to query these points, which is what we've been doing so far, then you're stuck, right? To figure out which point is a +1, you need to essentially query all the points until you find the 1 point that happens to be a +1. So it seems like here we're stuck. So what can we hope to do? So a lot of the research in the machine learning community has been on trying to say, well, this is really like an adversarial scenario. Like this example here is really adversary. It doesn't look like examples we get in real life. Let's look on relaxing this worst case assumption and get some distribution-dependent learning. Now, what I'm going to talk about here is a different approach. We're still going to be in this adversarial setting to a large extent, but we're going to allow the learning algorithm to ask more informative questions about the data. Like, for example, here, I would allow you to ask maybe about points that are not one of these points that you got, but maybe some other points here or here that you can choose. So now let me call this active learning with enriched query. So where I'm allowed to ask other questions beyond the data point that I got. So we can ask, well, what type of queries can we ask? Well, if you allow arbitrary additional queries, then you can, of course, solve this problem by saying, I have n to the d possible solutions. Is my solution in the first half or the second half? Then you can solve every problem with binary search, but these are sort of ridiculous queries. So you want to make linear queries. You want to make queries that seem to be reasonable. So we will restrict ourselves to very simple queries that go slightly beyond allowing to query the points. So we're going to talk about something I'm going to call them relative queries. So imagine that you're trying to build some, restaurant recommendation app. We're trying to recommend for a user whether they're going to like or dislike a specific restaurant. So imagine your goal is to predict for every restaurant whether a user is going to like it or dislike it, plus or minus. So you can ask a user, are you going to like or dislike a restaurant? But let's say a user told you that they like Japanese, but they also like McDonald's. So you can ask them, well, which one do you like more? Do you prefer Japanese or do you prefer McDonald's? You told me you like both, but which one do you like more? Or here's another relative query. Here are 3 data points. Which one is the first one close to the second or the third? So these are relative query. And again, in this talk, to be very concrete, I'm just going to be focused on the first type, comparing 2 data points. So we're going to call these comparison queries. So what we have in general is what's called a concept class. H, all my classifiers, and I'm going to assume all of them come from having some underlying class of some real-valued function, like half spaces that we've seen so far, but maybe some other class like neural nets. So we have some underlying real-valued function, and the sign of this function is going to tell you whether you are plus or minus. And again, if you want to be concrete, this function is some linear function. So a label query is going to be asking, here's your data point xi. One of the data points you got is a sign of f positive or negative. A comparison is going to tell you, here are 2 data points, xi and xj, which one got a higher value. So notice that both of them are still Boolean value, or maybe they have 3 values. They don't get arbitrary answer sets. But now I'm allowing you to compare the value on 2 data points. And my question will be, does that give you any additional power? So now let me go again to this example of active learning in 2 dimensions, and I'm going to show you why allowing to compare 2 data points is actually going to be useful in this setting. So again, this is a problem. I'm just recalling the problem again. You are given n points in 2-dimensional space. They're labeled plus or minus. You want to figure out what is the labeling. But now you're allowed to make 2 types of queries. You're allowed to label points, you can point to one of these points, ask either is it plus or minus, or you can do a comparison query. You can choose 2 points and ask which one is closer to the line. So I want to show you why using just these 2 types of queries, you can go back to solving this with other log n queries. So similar to the performance of binary search, but now we sort of generalize binary search from 1 dimension to 2 dimensions. So let's see why. So here's going to be the algorithm. And the algorithm is going to look very, very different than the standard binary search. So again, what is my input? It's the size n point set that I know. What I don't know is the labeling, and there is unknown line. So here's the algorithm. First, I'm going to just randomly sample 28 points. Well, why 28? It seems like a weird number, but you'll see why. So 28 actually is going to make this work. You can make this work with less than 28. I mean, the best we can prove is 20, but you need some constant number of points. Let's stick with 28. So you sample 28 points. And then you just label them. So you make 28 queries, and you label which ones are below the line, which ones are above the line. And now we're going to do the new thing. We're going to find in each side the closest point to the line. And here we're using comparisons. So for example, go over all these red points. We ask which one is the closest to the line. So we use this comparisons oracle to find that. But again, we just need some constant number of queries to do that. And here's where we can make leverage or leverage that. Let's build cones. So I'm going to take all these red points and take the convex hull. And I'm going to here, I know this one is closest. And I'm going to build this cone, going through the red point closest to the green line and through these other 2 that define this cone. So I know that all these red points lie in this cone. And then we do it similarly for the blue points. And I can now just forget all the other points in this cone. I just care about the 3 points that define the cone, plus the point I know that's closest to the cone, the line. And now here's the main observation. All the points in this cone must be labeled plus. Why? Because if I have these 3 points that are all labeled plus, and in addition I know that this point is closer to the green line compared to this point or this point, then just a simple exercise to check that all the points here must be plus. There's nothing else that can happen. The green line cannot intersect this cone. And still for the blue cone, so we do that. So now we go back to all the points, and every point that happened to be in this cone, we just labeled it to be plus, so we can just remove them and continue. So now the main question that you might ask yourself is that, why is this guaranteed to work? I mean, maybe also here there are adversarial configurations of points where when we do sampling and this labeling and this inferring, you only learn a small number of points. We need to repeat this many, many, many times. Why suddenly is this algorithm guaranteed to label many points at every iteration? So I'm going to claim to you, and we're going to see the reason in a few minutes, that this is guaranteed to work. So in any iteration with some constant probability, you're going to label some constant fraction, let's say half, of the unlabeled points. And this is for any configuration of points. This is the worst case guarantee. So each iteration only makes a constant number of queries. So overall, we need with high probability something like log n queries to make. So we have log n iterations. Every iteration reduces the number of points that we don't know yet are labeled by a constant factor. And in every iteration, we make a constant number of queries. And you might wonder, why does this work? Well, it might seem like it has to do with the geometry of the problem. But as I will shortly show you, it has nothing to do with geometry. It really is about combinatorial structure, not geometry, that makes this work. So let's see why. So the main thing that makes this work is this definition of something that we call inference dimension, which is basically asking what is a dimension that allows a learning algorithm to infer information if it is allowed to make more powerful queries compared to what it's trying to learn. So here's our goal. Our goal is to define some combinatorial dimension. And again, think of VC dimension as a model here, maybe. But I want a model, a dimension that allows for some asymmetry. So I want a learning algorithm that wants to learn something, like the labels of these points, but it can ask maybe more elaborate questions, like it's allowed to maybe compare points. So like we want to learn labels, but we're allowed to ask about labels, or we're allowed to ask about comparisons. So we'll try to define some dimension, some combinatorial dimension that allows us to capture that. So the next few slides are going to be slightly technical, but then I'm going to have some examples illustrating it. So bear with me. So again, for simplicity, let me focus on comparison queries here. So I have some domain X and some general concept class, like maybe linear classifiers, doesn't have to be. And I'm assuming every classifier in my class can answer two types of questions. It could label points, or it could compare 2 points and give me an answer. Let's say plus or minus, or maybe plus, minus, or 0. Doesn't matter. Now, what do I mean by inference? Okay, so this is my first technical slide. So I have a set of points. X, remember, X is my set of points. S is a small subset I chose. H of S is going to be all the answers to all the questions I could potentially ask about points in S. So for example, if I allow labels, it's going to be all the labeling of points in S. And if for comparisons, all the comparisons for all points in S. And given a point X in my data set X, I'm going to say that my small sample S infers my point under my classifier H if the following thing holds. Given this information H of S, given all this labeling of points in S and all the comparisons, it uniquely determines the label of the point X. Okay. And here's my last technical slide. And again, this might seem very abstract, but we'll read through this together, and then I'm going to show you 2 examples that are going to illustrate it. So this is what we call the inference dimension. It's like a worst-case guarantee. It's a minimal dimension K such that the following thing holds. Every sample of K points contains a point in it whose label can be inferred from the other points in this sample, but for these other points, I'm allowed to use both labels and comparisons. So maybe with some more notation, for every set S in my data set of K points, and every classifier that I could potentially have in my classifier set, there is some point in S such that the remaining point in S infer this last point under H. Note that this is sort of like a non-deterministic guarantee. So I'm not saying that I'm allowed to know this, I can figure this point efficiently. I'm saying, given this set of K points, do all the queries you want. At the end, there is one point I can remove from the set because I can infer its label from the other queries, labels and comparisons on this set S. So now let me show you 2 examples that hopefully would explain this definition that is, at this point should be very abstract. So let's first look on thresholds in 1 dimension. And I'm claiming that in this example, this dimension is 3. So the inference dimension of thresholds in 1 dimension is 3. And here actually we only need labels. We don't even need comparisons. Why? Well, if I have 3 points on a line, let's assume that first all of them have the same label. Maybe they're all plus. Well, if I know they're all plus, then you can just erase this middle labeling because we don't need to know it. We can infer it for free because if I know this point in the middle has a point on the left that's a plus and a point on the right that's a plus, then the point in the middle must be a plus. No other way about it. Well, the other scenario is they have different labels. So 2 of them get the same label, and then the third one gets a different label. Let's say it's a plus, plus, minus. Well, in this case, there's always one of the boundary endpoints that can just erase its label because they can infer it for free, right? So in this case, they can just erase the label from the left point because you can deduce it from free from the other 2 labels. So in 1 dimension, this dimension is 3, and you can actually verify it cannot be brought down to 2. So for 2 points, all the possible 4 labelings are possible. Now, but here we didn't use comparisons. But let's go to 2 dimensions and see that there we actually need comparisons. So in 2 dimensions, I claim that with comparisons, this number is at most 7. And in fact, if you work a bit harder, you can bring it down to 5, but let me prove 7. It's going to be easier. So if I have 7 points in the plane, let's assume for simplicity none of them are on the green line, then at least 4 of them must be on one side. Let's say in this side, the right side, they're all plus. Let's take the convex hull. Let's take the cone span this convex hull. Well, this cone is defined by 3 points, So one of these points must not be in the cone. It must be inside the cone. So, or maybe on the boundary, it doesn't matter. So I can just remove the label of this last point. So if I know that these 3 points are all plus, and in addition, I know the comparisons between all these 3 points, I can deduce for free that this must be a plus. So in 2 dimensions, 7 points are enough. So the inference dimension in 2 dimensions is just at most 7. And here's a general algorithm that works just based on this combinatorial dimension called the inference dimension. Let's say it's k from a concept class, but here's the algorithm. We sample 4k points whose labels are still unknown. We compute all the queries on this sample, all the labels, all the comparisons. And then we just do whatever inference we can. So then we go through all the other points that we don't know the label for and ask, can I, for free, infer the label of this point, given the data that I know so far? And you can see that for linear separators, so linear half spaces, this is basically solving a linear program. So you can do it efficiently, and you just do it for all the points, you infer the labels, and just repeat. You remove at every iteration all the points whose label you inferred, and then just repeat this process. And again, the theorem said that if the inference dimension is k, and you sample slightly more points, 4k, in every iteration, then with some concept probability, you're going to label half the unlabeled points in every iteration. And again, so we only need log n iterations here. And the algorithm in this 2-dimensional case was just a very special case because we said 2 dimension, this inference dimension is 7, 4 times 7 is 28, which is why we had 28 points there. Okay, so now the question is, well, so in 2 dimensions, we can bound this inference dimension. What about higher dimensions? In what general scenarios can we hope to bound this inference dimension? So let's go to now d-dimensional space. So the first thing I have to tell you is some bad news. Turns out that in 3 dimensions already, you can build instances, configurations, whose inference dimension is infinite. Meaning that there exists sort of, setting of endpoints in 3 dimensions that even if I give you comparisons, you will still need something like n queries to reveal their labels. And this example sort of looks like the bad scenario we had in 2 dimensions, sort of lifted into 3 dimensions in some suitable way. But the nice thing here, unlike the label case, is that we can actually prove that these counterexamples are pathological. So if you make some very mild restrictions on your data points, then you can get rid of them. And we can prove them in 2 scenarios. One is maybe more motivated by the next scenario. I'll show you its connection to complexity, bounded bit complexity, where I think that the points are sort of have integer coordinates that are not too big. And the other one is maybe more reasonable in machine learning settings, where I'm assuming no point is too close to the hyperplane, so the margin is something reasonable. And in both cases, we get sort of optimal bounds for the inference dimension, basically logarithmic in the bit complexity in some sense. And both of them give us efficient active learning algorithms. And so basically what we did here is we moved all of the difficulty in constructing these active learning algorithms to this combinatorial question of bounding the inference dimension. Now both of these 2 results are relatively technical. But at least we moved all of the complexity from the algorithmic side to the combinatorial side, which I think is very similar to what happened in passive learning with VC dimension, where bounding the VC dimension of a class allowed you for free to do various types of learning algorithms on it. So now let me move to something that is sort of, at least on the surface of it, would look completely different, but we'll see it's actually tightly connected, which is going to be problems that come up in fine-grained complexity. In particular, I want to focus on this one problem that people have been studying a lot for the last maybe 25 years, called threesome. So I'm assuming many of you have heard about threesome, but let me just recall this problem. You're given n numbers, that's your input, and you want to find if 3 of them sum to 0. So how can you solve it? Whether the super naive algorithm that takes cubic time, just trying out all possible triples. But if you think about it for 5 minutes, you can solve it in quadratic time using hashing. And that's the best that we know, basically. So you can ask, well, can we do better? And also, why should we care? I mean, this seems like this interview type problem, right? I mean, why should we care about this sort of innocent looking problem? Why should we care about improving quadratic time here? Well, the reason is that it turns out that for many problems in computational geometry, the best algorithms that we know are also quadratic. And in addition, three-sum embeds into them as a special instance. So there's a list of dozens and dozens of problems in computational geometry that if you can beat quadratic time for any of them, then along the way we'll have to find a better than quadratic time for three-sum. So it seems like a very convenient target to study. And in fact, this was noticed by Gajentan and Overmars, again, 25 years ago. And they actually conjectured that quadratic is the best you can do, maybe up to like low order terms, but that essentially you need quadratic time. So they conjectured that any algorithm for three-sum requires essentially quadratic time. And then more recently, in this area of fine-grained complexity, researchers have found connections of three-sum and other related problems to many, many other problems, where the best algorithms we know are quadratic or cubic, but not linear time. There are graph algorithms, dynamic data structure questions, and so on, many others. So this is what forms the core of this area called fine-grained complexity, where we identify several key problems that are in polynomial time, but not in linear time. And the goal is to ask, can we bring the complexity down to linear time, or either some inherent difficulty in doing that? Again, let's focus on three-sum. And I'm claiming three-sum is really a special instance of this point location problem that we've seen in the first part of this talk. Why? So here's how to formulate three-sum as a point location problem. So first the input. I'm going to think of my input not as n points, n numbers, but I'm just going to collate them at one vector in R to the n. My hyperplane is just going to be the following very simple hyperplanes. It's going to be all the ones whose normals are just 0, 1, where the number of ones is 3. So it's going to have all the vectors in 0, 1 to the n, with 3 1s and the rest being 0. So I have roughly n cubed hyperplanes. And again, the set is just the cell of the point, same as what we defined before. So I'm claiming x as a three-sum, naming there are 3 points in x that sum to 0, if and only if x lies on one of these hyperplanes, right? If there is a hyperplane spanned by EI plus EJ plus EK, where these are just unit vectors, standard unit vectors, where x is just orthogonal to this. So x lies on this hyperplane. So if I know all this vector of signs, and one of them is a 0, then I know x is a three-sum. If none of them are a 0, x does not have a three-sum solution. So of course, if I know this vector, I know more. But in particular, it's enough to solve three-sum. So you can ask, what can we say about this very special point location problem? So it turned out that this quadratic algorithm for three-sum can be converted to a quadratic linear decision tree for three-sum. So the depth is just a number of queries we make. And moreover, all the queries we make are just going to be asking about labels. We're going to basically ask at every query, here are 3 points, sum them up, is a sign positive, negative, or 0. And in a very influential paper in the late 90s, Ericsson proved that if you're only allowed to make these types of queries, then actually quadratic time is necessary. You cannot beat quadratic time. So this seems very promising. Maybe we can prove that three-sum requires quadratic time, at least in this model of linear decision trees. So Ericsson actually also proved that this is still true if you're allowing slightly more general queries, where you're allowing any 3 sparse queries. You choose 3 of your points, but you're allowed to sum them with some coefficients, positive or negative, then ask about the sign. So again, maybe it's true in this model. That'd be great. This would show that many natural algorithms in geometry, that can be phrased as linear decision trees require at least quadratic time. Well, this turned out to be false, because there was this breakthrough work 6 years ago by Gron, Lund, and Petty, who showed that, yeah, you can break for three-sum this quadratic barrier. So they gave a linear decision tree that gets something like close to n to the 3/2 queries. n is not 3 sparse, it's 4 sparse. So by allowing more general queries, they were able to break this quadratic barrier. And what I want to show you now is that using this inference dimension framework, we can improve this to near linear. So up to this polylog terms, we get to near linear time complexity, and we need to have slightly more general query, 6 sparse and not 4 sparse. Okay, but still constant sparsity. And in fact, there is nothing special about 3-sum. The same technique exactly would work for many, many problems in fine-grained complexity that people studied in this model, like K-sum, all Perseus path, and so on. And for all of them, we get basically the optimal bounds up to maybe log or log squared factors. And in this, so what do we learn? We learn that in this combinatorial model of linear decision trees, actually 3-sum is easy. So the 3-sum conjecture is false, which means that, well, if you're hoping to prove some lower bounds on algorithms, we need to somehow find a different approach. Or maybe you can view it positively and say, well, maybe this shows that this product is actually easy algorithmically, and maybe we can find like better algorithms. So let's view this dual problem to 3-sum. We said, remember that every point location problem has this dual active learning problem. So what is a dual problem what is the active learning problem for 3-sum? Well, it's the following problem. My data points are just all these 0, 1 to the end points with 3 1s and the rest being zeros. I have my input, this unknown hyperplane, and I want to figure out if one of these points lies on this hyperplane, meaning if the inner point is 0 for one of them or not. Now, these data points have bounded bit complexity, just 0s and 1s. So we can apply our inference dimension bound for bounded bit complexity and figure out that this inference dimension here is order n. And if you plug it into the framework, this would give us an active learning algorithm with near linear number of queries, which again, by this duality, would give us this linear decision tree with a near linear depth. So we just get it for free for this active learning framework. So what happens for arbitrary point sets? So just very briefly. So I will tell you that this inference dimension framework breaks down in some pathological situations, even in 3-dimensional space. So you can ask, at least for, I'm doing complexity theory, I care about pathological scenarios as well. What can we say in general? For arbitrary point sets, we're making no assumptions on them. So here is a table summarizing what people have known. And this works mostly in the computational geometry community. So this starts from this breakthrough work of Hufdermeyer in the early 80s that showed that for this knapsack problem, you can do something that depends only polynomially in n and not exponentially, even though this is an NP-hard problem. And then Meisner realized about 10 years later that you can generalize this approach to solve a general point location problem with poly-D behavior and log n. So you get the optimal behavior on the number of points, and some polynomial depends on dimension. And remember, the lower bound was d log n. So the question is, should we depend on the dimension polynomially or linearly? So there have been a sequence of works improving the dependence on dimension. And we had this work assuming something nice, but this is not for adversarial scenario. So we have this new work. This is with Hopkins, Kane, and Mahajan, that's showing that for arbitrary points, we get very close to this lower bound, but we still pay something depending on d that is not quite what we were hoping to pay, but still is, in some sense, near linear. In some other sense, we still want this to be polylog d and not this sub-polynomial dependence, but that's the best we could get so far. So, but again, for the sake of time, let's just skip that and just summarize. So what I showed here is this point location as this sort of way of connecting problems in different areas. So it's starting from problems in geometry, computational discrete geometry, connections to machine learning, active learning. We've seen this inference dimension as a way of analyzing these problems when we allow a more rich type of queries. And we've seen how this allows us to understand questions in fine-grained complexity, like 3-sum. I just want to spend my last 5 minutes talking about 3 types of open problems here. And again, there are many other ones, but I showed them 3 types just for concreteness. First question, which I really like, is can we match the lower bound? It's d log n. Now, notice that the lower bound that we proved is for any query type where we only have a small number of answers, like 2 or 3. while for upper bounds, we are very restricted the type of queries to just be linear queries. So can we match this information theoretical bottleneck or not? So we know that we get close to it now by sort of a very complicated algorithm that is randomized and various caveats. I'm really hoping that there should be either a simple algorithm here that solves this problem deterministically, or some reason why it can't exist. I really am hoping that because this is like a very simple combinatorial question, hopefully there should be a simple combinatorial solution. But so far, it's probably been studied for like close to 50 years, maybe 40 years, and we don't know of any such an algorithm. The second question is, can we hope for these techniques to help us actually speed up algorithms for three-sum or for other problems, or core problems in fine-grained complexity? So far, people have used these techniques to get some polylog savings, but not better. Can we hope to do better? I don't know. In particular, for threesome, can we hope to solve it much faster than quadratic time? Or are there other bottlenecks not related to this combinatorial linear decision tree model that you could hope to exploit? And the third one is maybe slightly more technical, but maybe slightly more approachable, is let's consider a threesome instance, and numbers, and let's try to make a problem easy. Let's think about the NP or co-NP version of that. So the NP version will be, given this input, prove to me that there is a solution so that it is easy for me to verify it. And that's very easy. If you know three numbers here that sum to 0, you can just tell me their indices, and I can very efficiently just sum them up and verify they sum to 0. So the NP complexity is linear. What about the co-NP complexity? How easy it is for me to verify that it has no solution? So let me make a conjecture that says that, and I'll try to explain why I believe this is true, that there should be a proof that there is no solution, that they can be verified in near linear time. And the reason I believe this conjecture is because the way we prove our inference dimension result is actually we know that there is a certificate that is easy that can be information theoretically verified that there is no threesome solution, and also it has only linear lengths. But we don't know how to do it algorithmically efficiently. But I believe there should be a way. And also, I want to mention that this is also important for understanding various types of fine-grained reductions, and this has been sort of studied in great depth in this paper of Carmosino, Gao, Impagliazzo, Mihajili, Paturi, and Schneider from 4 years ago. And in particular for threesome, they show that there is a faster than quadratic time to verify no solution. They give an algorithm in roughly n to the 1.5 time, assuming something about the input. So not for arbitrary points, but for like small integer points. But still it shows that the co-NP complexity is faster than the P complexity, which is quadratic, the best as far as we know. That's my third question. Again, there are many other more technical questions here that people have asked, and maybe we can discuss in the open problem section, but that's it for now. So thank you.
Thanks. Are there any questions? Once again, you can ask questions in the chat box, or you can just unmute yourself and ask.
Hi, Shachar. I have a question for you.
Yes.
This your result for active learning, does it work for like K-way classifier as well? Or do you know like what kind of what would be the
Yeah, I mean, there's nothing special about binary.
Okay.
I mean, it is really about asking, given some data or given some information, can I deduce some other data or not? Now, if it's binary, you can use linear programming. If you have several answers, you might want to use some other algorithm for this deduction, maybe some combinatorial algorithm. There's nothing special about binary. Just
okay.
Okay.
Yeah. Thanks.
Also, maybe one thing to add is that we've had some works extending some of these machine learning techniques to when you have some noise in the data, but the general question of agnostic learning is completely wide open.
Okay, thanks.
I have a question. So can you say something about the pathological cases?
Yes, yes. So if you remember this example from 2 dimensions, all these points on the circle, so basically you just lift them up into 3 dimensions, but you lift each one to like exponentially higher height to some extent. So roughly it looks like so the distances from your hyperplanes are not very, very far apart. And you sort of need to play with it a little bit to get this to work, but that's roughly how it looks. But the point is, in this case, the points both have exponential bit complexity, and also they have, or maybe, I guess maybe they need, the exponential precision, and also some of them are extremely close to the hyperplane, while others are very, very far apart. So they violate both the margin assumption and the bit complexity assumption. But I think a very natural question to ask is, maybe, in the same way with comparisons, like a two-way query that solves this two-dimensional product, making no assumptions, maybe there is like a three-way query you could make that solves this three-dimensional problem with no assumptions. And I think this should be true, but I don't have a conjecture. I mean, I don't even know what is the correct three-way query to make here. I mean, we had various approaches that we have counterexamples for, but I still think there should be some three-way query that should work here. But I don't know what it is.
Okay, thank you. Maybe I'll ask one more question. Why is the inference dimension 5 instead of 7? How do you show this?
This is a good question. So I think Daniel at some point showed it. I don't remember why, but sort of you use a linear program to also deduce information on the other side of the points. So you don't just use the points on, let's say if I have 4 points on one side and 3 on the other side. If you just want to use these 4 points and you have to have 7, if you're also allowed to use comparison with the points on the other side, then you get it down to 5. But I was saying it doesn't, I mean, it doesn't really. It's like asking you, but then if you try to translate this into, does it actually make sense? It's of, no, you like this restaurant and you hated this restaurant, but you really like this one more than you hate the other one. So it's not a very natural question to ask.
Sure.
But maybe if you have ratings, if you give a rating to restaurant 1 to 10, then it makes sense to infer that from your labels.
Any more questions? Okay, well, if there are no more questions, so thank you again, Shachar, for the very nice talk.
Thanks.
Great. Yeah, so now we have another break, and we'll be back here with the next session in about 20 minutes at 10:20 Pacific time. So see everybody then.
Thanks.